Hello everybody, welcome to section 11.4 where we continue our study of series tests, and we're going to look at a couple new ones today. The comparison tests, there are actually two of those. So let's get started. So the comparison tests are used to compare a given series with another series known to be either convergent or divergent. So if you look at this series we've got right here, this one is a geometric series, which means if it's geometric as a ratio, which means I can take this number and multiply it by a ratio to get here, and use that same ratio, multiply it by this number to get here, and then here, and so forth. So if you look at it, it looks like we're multiplying by 1/3, right? So the ratio is 1/3. Also, the way you can find it at any time is just take one of these and divide by the previous one, right? Take any term, divide by the previous term, you get the ratio. Now, since r is 1/3, we know that this series converges. Since the absolute value of r is less than 1, right? Because r equals 1/3. Then we've got this other series over here. Well, this is term by term smaller than the known converging geometric series. So if I compare these two, there's 5 halves. 5 halves is smaller. 5/3, 5/4. 5/4 is smaller, right? Because the denominator is bigger. 5/9 and 5/10. 5/10 is smaller. So every term here is smaller, term by term, than each term here. So even though its sum is unknown, we could find the sum of this series. We can't because this is not a geometric series, right? This is definitely not a geometric series, but we know this series must also converge. It has to, because think about it. If these add up to a certain number, right, it converges. We can add this up and we get some number. Well, in this series is term by term smaller, then there's no way we could add these up and get like infinity or something, right? So that means that it would also have to converge. So since this is term by term smaller than this series, we know this series converges, then this has to converge. And then we've got something similar with this series. So this series, looking at it, nothing really stands out about this one, but it is term by term greater than the known diverging, or we could say, divergent harmonic series, right? We know this is the harmonic series, very famous series. This one diverges. In this series, look at term by term. 7's bigger than 1. 7 halves bigger than 1/2. 7/3 is bigger than 1/3, and so forth. This is term by term greater than this series, which diverges. So if this adds up to as high as we want it to go, like it goes to infinity, right? You can make it go as high as we want. It's unbounded. And this one is bigger term by term, then this one also would have to be able to go as high as we want it to go, right? So this series must also diverge. So we've got a series that diverges, meaning we could add it up as high as we want. We could say the sum is infinity. And this one is term by term bigger than one that has a sum of infinity. So this is going to also have to have a sum of infinity. Okay, so it's so there's a couple examples where we're just doing a direct comparison. And then there's a little note here. Good series to use for comparisons to other series is the P series, right? The P series that we studied in section 11.3, which looks just like this. Okay, so this one converges if p is greater than 1 and diverges if p is less than or equal to 1. So it's an easy one to use for comparisons. And then we have our first test, the direct comparison test. Sometimes it's just called the comparison test, but there's another test in this section called the limit comparison test. So sometimes people will just call it the direct comparison test, just so there's no confusion. But the other name is fine too. The direct comparison test or the comparison test, they both refer to this. And we've just got a couple infinite series with positive terms. We're basically saying if this series B sub n converges, and a sub n is less than or equal to this b sub n for all n, well then a sub n, series a sub n also must converge, right? B sub n converges. You could think of it as it adds up to a number, and a sub n is less than that for each term, so a sub n also must add up to a number, right? It must converge. And the other side of that is if b sub n diverges. So let's say this series b sub n goes, you could add it up as high as you want. It diverges, goes to infinity. And a sub n is bigger than, right? It's greater than or equal to b sub n for all n. Then a sub n is also going to have to diverge. So those are the two pieces of the direct comparison test. So now let's take a look at some examples and see how these work. So if we look at this series right here, 1 over the square root of n minus 1, don't you think long term it probably looks something like maybe 1 over the square root of n, like long term? And this one we know something about, right? That's really 1 over n to the 1/2. That's a p-series, which diverges. So long term, probably this acts like this one, right? So it gives us some sort of idea. That's not enough to make our argument, but it gives us an idea of what probably happens. So here's how we can do a comparison test. All right, so I'm going to compare to. With a comparison test, we need to say what we're going to compare to, right? So I'm going to compare to this series, 2 to infinity, 1 over the square root of n. Because this is equal to 1 over n to the 1/2. This is a divergent p-series. Divergent because p is less than or equal to 1 in this case, so we know it diverges. And then we can notice something. I'm going to note that when I compare these, if I have 1 over the square root of n minus 1, and I compare that to 1 over the square root of n, well, this denominator is smaller than this, right? This denominator is smaller, which means this thing would be bigger, right? Because the numerators are the same. So if this denominator is smaller than this denominator, then this is going to be bigger. And this would be for all n greater than 1. Okay, so we're basically saying, okay, we've got this divergent p-series, right? If I keep adding this up, I can make it go as large as I want it to. It goes to infinity. And we found something that's even bigger than that, right? This series, term by term, is bigger than this divergent series. So the conclusion is this also must be divergent, right? It's bigger than one that goes to infinity. So, so it's going to have to also go to infinity. So then we can say something like this. We could even use a word like thus, if you would like. Let's say thus, this series n equals 2 to infinity, if 1 over the square root of n minus 1 diverges by the comparison test, or direct comparison test if you prefer. Okay, so notice something about this. When we're going to do these tests for convergence or divergence, we need to mention the test we're using. I'm using the comparison test. And then, if I'm going to use a comparison test, I need to mention the series I'm comparing it to and tell what I know about that series, right? So we need to mention these things when we're doing these convergence tests. So I'm doing a comparison test. My conclusion is our series diverges. You always want the conclusion. And since I'm using the comparison test, I tell the series I'm comparing it to, I tell that I know this series diverges, and then here's my argument, right? So we need these three pieces. We need the name of the test we're using, we need our conclusion, and we need the argument we're using, which is right here. And in the case of using a comparison test, we need to mention the test we're comparing it to. Okay, so what about this next one, which looks very similar, right? It looks similar, but this one's going to have a problem. All right, now we can see long-term, this probably long-term x like 1 over the square root of n, just like this, right? Because if you're putting like a billion in here, adding 1 is probably not going to be a whole lot different than this one here, right? So probably it acts just like this one. But we can't use the argument we used above. Because look, if we did. If we say something like 1 over the square root of n plus 1, and I try to compare that to 1 over the square root of n, well, in this case, this denominator is bigger than this. So if the denominator is bigger, it means the whole number is smaller, because again, they have the same numerator. Okay, so this argument won't work here. This diverges, this series, if this is the nth, the general term of the series, this series would diverge, but it's bigger than this one. So I can't conclude that this one must diverge because it's actually smaller. Maybe it converges, right? So this works great here because this is bigger than a diverging series, but this is smaller than a diverging series, so it just doesn't work. Okay, but probably this is going to act very similar to this long term. So even though we can't do a direct comparison test, this direct comparison test won't work because this is going in the wrong direction. But there could be a test that we could use. Right, we've got, so our intuition is this probably diverges because it probably, like long term, we know it's going to act pretty much like this one because they're very similar. We know this one diverges, so this one probably diverges. So we can't use direct comparison, but we've got something else we can use. We've got something called the limit comparison test. It works great in cases like this. So in this case, you know, it's difficult to establish this idea, or maybe we can't show this, but we have an idea that we think we know what our series does. Well, then we can use a limit comparison test. So suppose we've got a couple series here and they have positive terms. Well, if the limit of a sub n over b sub n is equal to some number greater than 0, then both of these are going to converge or diverge. So what will typically happen is we'll be interested in maybe a sub n, but we know something about b sub n. So then we can do a limit comparison test. And the next two are really very much more obvious. So let's say we know b sub n converges. We take the limit of a sub n over b sub n, and we get 0, which means that this one in the bottom dominates, right? The denominator dominates so that between the two of them it goes to 0. So b sub n dominates a sub n, and b sub n converges. So then a sub n is going to have to converge, right? This goes up to, this converges, so it has a sum. This has a sum, and this one is so much smaller than this sum that the limit is 0. So if this converges, then a sub n also has to converge. And likewise over here, if b sub n diverges, but in this case, it's dominated by a sub n, so the limit of a sub n over b sub n is infinity. So this numerator is dominating the denominator, and the denominator diverges. So, like you could think of it as this denominator, that series goes to infinity and is dominated by a sub n. So a sub n also must go to infinity. So this is the limit comparison test. There's 3 different parts to it. Typically, we use this first part right here, and this just says that if the limit of these two is a number, it's a positive number, then they do the same thing, right? They both converge or both diverge. So with this in mind, let's go back to that other series and see if we can figure this one out. So this series, we saw we couldn't use the old argument. We couldn't use a direct comparison. Let's just try this limit comparison. So in a case like this, we would say something like, we're going to let b sub n be 1 over the square root of n. Okay, so because then we know that this is equal to 1 over the square root of n, which is a divergent p-series. Right, and I'm choosing this one because we suspect that this one probably does the same thing, right? So then we can use this, we can basically use this limit comparison test. So we can say the limit as n approaches infinity of a sub n over b sub n equals the limit as n approaches infinity. Now a sub n is our series, right? This is our series, that's a sub n. So I'm going to say 1 over the square root of n plus 1 divided by b sub n, which is the one that we think our series acts like. And then, of course, we have a fraction, but instead of a fraction divided by a fraction, I'm going to do a fraction times the reciprocal of the second fraction. So that would give us the limit as n approaches infinity, 1 over the square root of n plus 1 times the square root of n over 1, which is equal to the limit as n approaches infinity of the square root of n over the square root of n plus 1. And in this case, we've got infinity over infinity. So we could divide by the highest power in the denominator, which is equivalent to multiplying by 1 in this form. Right? And then when we do that, we will get the limit as n approaches infinity of 1 over, 1 plus 1 over the square root of n. Now when we take this limit, as n goes to infinity, this term can be made as close to 0 as we want to, so that the limiting value of this term is just 0. So this term goes to 0, and we end up with 1. We take the limit, we get 1 over 1, which is just 1, which is greater than 0. So it's greater than 0, and therefore we could say that to make it a little quicker, I'm just going to say our series, meaning this one right here, our series diverges by the limit comparison test. So we are mentioning the name of the test, right? We need to mention the name of the test. We need to mention our conclusion, which is our series diverges, this series diverges. Here's our argument, and since it's a comparison test, right, limit comparison test, we need to mention the one we're comparing, which is 1 over n, and that it's a divergent p-series. Okay, so hopefully that makes sense, but I know you're probably thinking, sure wish we had a couple more problems. Well, look at that. You are welcome. There's a couple right there. So let's take a look at example 5. So we got this series here, and what you want to do a lot of times is just kind of get a feel for what it probably does long term. So I'm just going to think about first let me just expand this and see what we get. So this is equal to n equals 1 to infinity, 2n plus 1, then you get n squared plus 2n plus 1. And then I'm just going to think, this is just kind of thinking for large n, right? For large n, just to kind of think what would happen with 2n plus 1 over n squared plus 2n plus 1. If we get really huge numbers, well, the numerator is going to be dominated by 2n. This one won't really matter when n is just a huge number, right? And down here, the denominator is going to be dominated by n squared, because we could make n squared as far away from 2n as we want to, just by making n big enough, right? So for large n, I'd say this behaves like probably 2n over n squared, right, which is 2 over n, if you just kind of keep going. So this will be dominated by, the numerator would be dominated by 2n, denominator by n squared, and this just simplifies to 2 over n. So 2 over n is just 2 times 1 over n, which is just a harmonic series, right, which diverges. So it's probably going to act like that series, probably. This is not enough to say it diverges, but it gives us some intuition about it, it probably long-term acts like the harmonic series. So what we can do is this. We can just say, so let's let b sub n, the one we're going to compare it to, be 1 over n, right? And we know that this series from 1 to infinity of b sub n is just the series 1 over n, which diverges, right? It's a harmonic series, or p series with p equals 1. All right, so we think ours diverges, and we're going to compare it to this diverging series. And then we do the limit comparison test. We're going to take the limit as n approaches infinity, a sub n over b sub n. A sub n is our series, which is 2n plus 1 over n squared plus 2n plus 1. Now, instead of dividing by b sub n, I'm just going to skip this step and multiply by the reciprocal, right? B sub n is 1 over n. So instead of writing divided by 1 over n, I'm just going to skip that first step and write times n over 1. Right, which is equivalent to this, but to dividing. And then algebraically, if we can clean this up. Oh, you know what? I forgot I need to squeeze in a limit. Okay, there we go. Now the universe is right again. This limit is n approaches infinity, so that would give us 2n squared plus n. Down here we get n squared plus 2n plus 1. And then the way we'd typically do this in a Calc 1 class with these, when we have an infinity over infinity, right? Take the limit, we get infinity on top, infinity on the bottom. So we divide by the highest power in the denominator, which is n squared. So we have this. This will distribute through these terms. So this will give us the limit as n approaches infinity. And we'll get, let's see, 2 plus 1 over n on the top. And on the bottom we get 1 plus 2 over n plus 1 over n squared. Okay, so now we take the limit. And basically all of these terms are going to go to 0, right? These will all go to 0. When we take the limit, we can make all of these as close to 0 as we want them to be. We just get 2 over 1, which is just 2, which is greater than 0. So our series, 2n plus 1 over n plus 1 squared, diverges by the limit comparison test. LCT, not to be confused with TLC. That was hip hop group from the 90s. Do you guys know about the 90s? I think T-Boz was the cutest one, by the way. But okay, LCT, not TLC. Limit comparison test. And look at what we did. We mentioned the name of the test. Our conclusion is it diverges. And since it's a comparison test, we need to say what we're comparing it to, right? We're comparing it to the harmonic series. And then here is our argument right here. Okay, so hopefully that one made sense. So example 6 looks a little bit different. We've got 1 plus 2 to the n, 1 plus 3 to the n. So again, I'm going to think like long term. Let's try to get a feel for what it looks like long term. So long term is n gets really huge, probably the 1 isn't really going to matter, right? Long term, this numerator is going to look like 2 to the n. Denominator will look like 3 to the n because he's just like 2 to the billion plus 1, pretty close to 2 to the billion, right? It's not going to be a big difference. So long term, we're going to have something like 2 to the n over 3 to the n, which is 2/3 to the n, which looks suspiciously like a geometric series, right, with r equals 3. So let's do that. Let's let b sub n be 2 to the n over 3 to the n, or in other words, 2/3 to the n. Okay, and then we know this. We know that the series with b sub n is this series, And this converges. This converges because it is a geometric series with r equal to 2/3. Remember, when the absolute value of r is less than 1, the series converges. Okay, so we're going to compare it to this. So let's do the limit comparison test. We take the limit as n approaches infinity of a sub n over b sub n, which is going to be the limit as n approaches infinity of, let's see, 1 plus 2 to the n over 1 plus 3 to the n. And once again, instead of dividing by b sub n, instead of dividing by that, I'm going to multiply by 1 over. So I'm going to multiply by the reciprocal of b sub n, which would just be 3 to the n over 2 to the n, right? 3 to the n over 2 to the n. And then I'm just going to multiply this through. So this is equal to the limit as n approaches infinity. So as this comes through here, I'm going to get 3 to the n plus 2 to the n times 3 to the n. Well, since the powers are the same, that's just going to be 6 to the n. So this will be 3 to the n plus 6 to the n. And then the denominator will get 2 to the n plus 6 to the n. Okay, now this is one that is a little unusual. I'm going to do something here that will sort of make sense because it's kind of like what we typically do when we say divide by the highest power in the denominator. This is a little different, but let me try something here and see if you think it will work. 1 over 6 to the n, 1 over 6 to the n. And I'm doing this is like, it's sort of the equivalent of the highest power in the denominator. It's the largest base, right? They all have the same exponent. So if I distribute this through here, we'll get something that will be easier to work with. So if I distribute that through, I'm going to get 3 to the n over 6 to the n. Right, so I will get 3 to the n over 6 to the n plus 1. And on the other side, I'm going to get 2 to the n, or I mean on the bottom in the denominator, plus 1. Okay, well this is the limit as n approaches infinity. That is really 3/6 to the n, right? 3/6 to the n, or 1/2 to the n, plus 1. And down here we get, we could write that as 2/6 raised to the n, or in other words, 1/3 to the n, plus 1. Okay, and then we could do a little bit more here. This is the same as, right, like if you look at this, isn't this the same as 1 to the n over 2 to the n? And since that's just 1 to the n is just going to be 1, right, no matter how many n's there are. Or, sorry, whatever, however large n is, I'm sorry, it's still just the base of 1, right? So that's just going to be 1. So really what we've got is 1 over 2 to the n plus 1, 1 over 3 to the n plus 1. And at this point, we can take the limit, because as n gets bigger and bigger and bigger, 1 over 2 to the n is going to get closer and closer to 0, right? Same with this. So when you take the limit, the limiting value of this is 0, limiting value of that is 0. So we just have 1 over 1, which is just 1, which is greater than 0. So since it's greater than 0, if you look at our limit comparison test, we can say, so the series from 1 to infinity of 1 plus 2 to the n over 1 plus 3 to the n converges by limit comparison test. So again, the things we need to mention, the test we used, our conclusion. Since it's a comparison test, we need to mention the series we're comparing it to, geometric series. And then our argument is all this stuff here. Okay, so hopefully these are making sense. They don't seem too bad. It's definitely better than the integral test, right? That one is a handful. But let's see, we've got one more to go. All right, I don't know why this software refuses to look straight. I load it straight. As soon as you move it around, it gets crooked. So I don't know why that is. But all right, let's take a look at this one. And I just think long term, I'm just kind of playing around with it. Long term, it'll probably act like this, right? That negative one won't do much. And then this reduces. So this is sort of like 1 over n. All right, we know what that one is. That's a harmonic series. So I'm guessing that this one probably acts like that and probably diverges. So with this one, we can do a direct comparison test actually, because we could just do this. So let's look at this argument, n cubed over n to the fourth minus 1. This is bigger than n cubed over n to the fourth, right? It's bigger because this denominator is smaller than this denominator, which makes this thing bigger. And this thing is just 1 over n. All right, so we could just do an argument like this. We could say, okay, now this is true for all n greater than or equal to 2. We also know that n equals 2 to infinity of 1 over n diverges because it's a harmonic series. Or you could say p series with p equal to 1. But we know this diverges, and this is bigger than this. So if this one is bigger than a diverging series, then it diverges. So we could just say n equals 2 to infinity of n cubed over n to the fourth minus 1 diverges by comparison test. By direct comparison test. You could use a limit comparison test too, but it's quicker just to do it this way. So this is just some scratch work, just thinking what this probably acts like long term. But we're using a comparison test. Here's the test we're using. Here's our conclusion. Since we're comparing, what are we comparing it to? This one right here, the diverging harmonic series. And here's our argument. Our series is larger than the diverging series. Okay, so that's all we really need on this one, just in a comparison test. But what about this? What if we had this next example? What if we had n equals 2 to infinity of n cubed over n to the fourth plus 1? Okay, what do we do with this one? Can I do the same argument? Definitely can't, right? Because over here, n to the fourth plus 1 would be smaller than this. So although this one probably acts just like this one does and just like this one does, we can't do a direct comparison. So this would be the case, like the first example we looked at with a limit comparison test. Just do the limit comparison test. So sometimes you can't do a direct comparison because it won't work right, like if there had been a plus here. But you think it probably acts like this. Whenever you can't do a direct comparison, but you have a good instinct about what you think happens, just do a limit comparison. Okay, so that should be enough to get you started. So give them a try, and you know what to do if you have any questions. Just let me know.